that is thermodynamics. Yeah, so I hope this year will be good for your studies, and I wish you that. Putala hunad. Hello. Can you? Flashing. Flashing. Do you know what flashing means? Know what flashing means? Flashing in the sense. Do you have any idea? What flashing means, Puta? Okay. Let's say example. Example. Okay, let's say example. Flashing example, one example, let's say let's say if you have a flat metal plate, let's say this is a flat metal plate, and if you place a fire underneath, okay, so if you place a fire or a gas flame, okay, flame underneath, chat is there. Yeah, thank you, Bhutana. Happy New Year to all of you. If you put a flame underneath, let's see, I'm going to put a flame underneath. I'm going to put a flame underneath. Okay. And this is your maybe a kind of a hot plate. You are using for cooking or whatever may be. Let's say this temperature of the plate is at a very high temperature. Let's say temperature, suddenly nothing is here initially. Let's say temperature is 120 degrees Celsius. Okay, let's say this is 120 degrees Celsius temperature here on the plate. Okay, 120 degrees Celsius. Quite hot. Okay, temperature is 120. Quite hot. Okay, so this is a situation. So this is a kind of a hot plate. Hot plate on a flame. Okay, on a flame. This one. Nothing is here. Let's say suddenly, not say suddenly, you are letting one drop of water. Okay, one drop of water falling down. Okay, one drop of water falling down. Imagine the situation. Falling down. Okay, and later we will learn why we are learning about flashing, falling down. So suddenly this will hit this. Okay, immediately hitting, as it is water. Okay, as it is a drop of water, what happens is once hits immediately, today my internet connection is unstable. This becomes something like flattening. Okay, this becomes flattening. Too much you cannot see. Flattening. So I make this a bit big. Okay. To match with the size maybe. No, let it be. Yeah. This becomes flattened. Yes. And what happens immediately? Once this hit flatten at no time, okay, this turns into a huge, okay, a huge bubble like this. Okay, this immediately turns into a huge bubble with no time. Okay, so I just put the color, maybe it's like this. No time. Yes. Yes. So all of a sudden, here to here, the situation from here getting flattened and turn into big bubble. Okay, big bubble. So if you think of this time duration, okay, this time duration I put as delta t, okay, delta t. Delta t. And this is almost, okay, this is almost like 0. Okay, delta t is almost like 0. Delta t is almost like 0. Means it takes no time. Okay, almost 0. It takes no time. So let's notice the temperatures. This bubble may be, this a drop of water. Let's say this is at 25 degrees Celsius. 25 degrees Celsius. Okay, so just about to hit at 25 degrees Celsius. Delta T almost 0 means one way you can say this. At no time. Okay, at no time. at no time. This 25 degree will change to 120. This one time lesson होता है 120 and immediate. This sudden energizing, this is unbearable for this tiny drop. Okay, even a big drop sudden, it will be a bigger one again. 120. So let's say this is 20 degree. So suddenly all 100 degree rise. 120. What happens is this turns into gas. Almost. Okay. At no time. You know that this is under ambient. Your pressure is 1 bar and boiling point of water is 100 degrees Celsius. Okay, 100 degrees Celsius. So here it is above 100 somehow. Okay, this is above 100. Even at 100 this can happen because this starts boil immediately. I just put little over 100. Okay, and is 100. Okay, so at 2 bar, I think at 2 bar water boils at 120 if I'm not mistaken. I have to check it. Okay, let me check it. I will go to cool pack. I will share the screen. So I will go to cool pack. Saturated. So I will take water. Water. This are for refrigerant. So pressure 2 bar. Let's see. See pressure 1 bar. Here I'm circling here. Pressure 1 bar, it is 100. You can clearly see this. So where is 120? So 1 bar it is 100 and 120 is at 1.98. Okay, 1.98, 120. 2.04 by 121. So I'm right. Thank you, Buddha. Okay. So you can say that. Very sorry, you couldn't hear. So you can see when this, at no time, this tiny drop of water subjected to high temperatures turns into a huge gas bubble, and the volume is more than 1,000 times. Okay, volume is more than 1,000 times. And even during this test, even you can hear some noise. Charas galahin තාච්චියකට තෙල් ටිකක් හිම දානකොට for a hot plate when you put some little water, not big amounts, you hear a thrust noise. Or even for the boiling oil, when you put some, let's say, onion or whatever, again you see here, you see there. Because that oil may be so hot that it is almost close to the fire point. Okay, sure, above 100 degree that oil. When above 100 degree, when you put water boiling is at 120. So above 100 oil. Signal not stable for that today. So your pan is, let's say the oil pan. Oil is above 100 degree. If you put little drops of water, tiny drops, a few drops of water, so water will come very close to the oil temperature. Let's say oil is at 120. The same thing happened, thrust noise, because the water suddenly becomes vapor and volume is bigger, so the taking the space is the noise you are experiencing. Okay, this is what we call flashing. Okay, so you have learned a very good lesson about flashing. So it's a sudden volume increase when liquid evaporates at no time. Okay, so flashing, so the liquid evaporates, normally we call boiling. Okay, so slow evaporation, boiling and flashing, it's different. Okay, boiling and flashing, it's different. Okay, so boiling versus flashing. So boiling is a different one. So for boiling, you are considering bigger amounts of water. Okay, bigger amounts of water continually supplying heat. Okay, continuously supplying heat. I hope you can see the screen now, Buddha. Okay, so boiling. So boiling is different, you know this. These are simple experiences you have. Okay, these are the simple experiences you already have. Okay, so you know the difference. But when it comes to science and technology, these are very important. Even cooking, there are sciences, there are technologies. Okay, boiling, there are sciences, there are technologies. Okay, nice, very nice slide. Okay, very nice slide. So you have learned this. Very good. Okay, so you know what is flashing and what is boiling. Boiling is different. If you put this flame and then you put some kettle with some water, you can see the boiling after some time. Slowly the temperature rises in the boiling point and it starts boiling. Okay, it's time taking. Boiling is time taking. Okay, so that is the difference. Time taking process, boiling. This one, no time. Okay, no time. Okay, and I'm very sorry today the signal quality is extremely bad. I don't know what to do with this one really. Extremely bad signal quality, but we have to be patient with that. No choice. We have to be very patient today. Okay. So this is the situation. 2 hot plates. If I can put more contrast color. Oh, that is not very good. Ah, that looks okay. Good, eh? Yeah. Good. Yeah, I believe you can understand this. So you know boiling, you know flashing. And in refrigeration also there is flashing taken place, but later we will learn this. Okay, later we will learn this. So now I'm going to take one previously done slide here with the purpose. Compression, your capillary here, metering device, somehow here compressor is the dispatch. Okay, compressor is the dispatch. The transport for unloading at the condenser, and then the transport returning for loading here. Okay, so I'm going to have the same but little bit different way. Okay, so I will take this in another way, something like this. It's the same cycle. You see what I'm doing. Eh? I want the above for unloading. This. I consider this for loading. Then, sorry. This is your evaporator. Okay. This is your evaporator. Just put it down. Don't worry, Bhutali, you have to be very patient today because of the signal issue. So when you evaporator put this way, your transport should come here. Dispatch. Your controlling of the flow is here. I make this little smaller. I make this little smaller. Okay. Put this up a bit. So this evaporator is something like, it's a tunnel for the transport. It's a tunnel, something like a tunnel. Transport is moving, so this is like a tunnel. Eh? So for receiving heat or for loading, if you cannot see the display or if you cannot hear the here, please. So you are receiving, the transport receiving here, the transport releasing, unloading. Okay, unloading. So loading. Very nice. For a stable flow, so you may consider not only for loading but for unloading. Both you may consider. This 1 kg truck, loading, as well as for unloading. Unloading, let me change the color to bit darker. Okay, loading is, let's say, bit bluish. Okay, like this. So far okay. So far okay. So 1 kg trucks. Yeah. Okay. 1 kg trucks. So as we learn, that day, the W is here. Compressor work input. Actually, that's power provided by the dispatch. We call it dispatch at the moment for circulation. And also the other two, let me take QH and QL. Because this mind mapping is important for you. QL is here. Okay. QH and QL. And it is obvious this QL receive, this QL exits. Okay. So I will take this as a new slide. QL exits and join with W and going here for QH. Is QL plus W. QH is QL plus W. And this QH is entering for unloading. and QH is unloaded and return back. Okay, so your efficiency term here we call, instead of efficiency, we call coefficient of performance, or COP. Okay, COP. Refrigeration. Okay, is QL divided by W. So this one. I hope you can read this. A little bit difficult, but on your displays, computer or even your smartphone, I hope you can see this. To see better, if I take this word refrigeration out, we can try with bigger fonts. COP is this. Yeah. Okay, I believe you understand this very well. So this is on the way to understand the transport, as I mentioned to you. Okay, so in understanding the transport, we talked about this last week. Using HFG for QL as well as for QO. Okay, so this is the point. Because latent heat is so important. I told you that by showing. Yeah. If you are using the sensible heat, temperature is rising, so your delta T is reducing. Okay, I hope you can understand. So when you have the latent heat, so what happens is this QL, okay, this QL when received by the transport, okay, when received by the transport, because here you have to have little practical sense as well. Through the capillary, this is coming. So I mentioned to you that in your room, okay, on this one. You can see here this evaporator is what you are seeing here, okay. So your 10 degree, so your 10 degree this stage learning is very slow, is really what inside here, okay, the 10 degree. The 10 degrees what inside here. The 25 degree is what outside here. Okay. So when you have 10 and 25, when you have 10 and 25, so it's the same unit here. So 10 and 25. There is a temperature difference. Okay, room temperature is 25 and this arrow looks too big. Then you have to be very patient today. You have a delta T. Okay, you have a delta T or a temperature difference is 25 degrees Celsius minus 10 degrees Celsius. That is today very sorry for that. I cannot help. Only thing is we have to exercise the patience. Delta T is 15 degrees Celsius. Delta T. You may notice this. Okay? You may notice this. Delta T. So, if we are using HFG, even here, this should be 10. Okay. Here, also it is 10. And your 25 degrees C. Of course, that's a room air temperature. So you can see it's the same. Okay, you can see it's the same delta T everywhere. So we have to get arranged the transport or the liquid flow like this. Okay, so if you look into the flow of saturation refrigerant, okay, or saturated liquid here, until it evaporates, the temperature remains the same. Okay, until this evaporates, the temperature remains the same. So if I get you refreshed, okay, if I get you refreshed, can you remember the Rogers and Mayhem? Rogers and Mayhem. The property tables. This is for water and steam. See your HFG here. Can you see this HFG? This HFG. So what is that HFG? That is what we are using. This HFG. So we are using this HFG. Okay, Buddha. This is the HFG we are using. Okay. So it is something like if you have the refrigerant entering here. I'm sorry, Buddha, today we have to live with this problem. Eh? So no choice. We have to live with the problem. Okay, Buddha. So initially, oh Buddha,
Sir, excuse me.
oh Buddha,
Sir, කියන කැඩිලි නෑ.
Buddha, hari, ඒක තමයි problem එක. Signal issues we have. Buddha, can you give me a second? I will solve the problem. Give me a second. Eh? So give me a second. I will try to solve the problem. Maybe I will look for a mobile connectivity. Let me see. Then Harida, is it okay now? Give me a second. Give me a second again. Oh, should be okay by now. Okay. Hope this should be okay by now. Okay. So this HFG means this HFG is relevant. This HFG is relevant for this kind of saturated conditions. Okay. Saturated conditions. That is very important to know. Saturated conditions. Saturated conditions. Saturated conditions. Okay. And of course, what important is liquid. Okay, saturated condition. Saturated liquid conditions. That is okay. So you may think that here is saturated liquid. Okay, saturated liquid. Let's see here. So you may have saturated liquid. Saturated liquid. Plus there should be vapor as well. Liquid plus vapor. So you have more liquid. Very small vapor. Okay. Or saturated. Very little vapor. Temperature is 10 degrees. If I put it here, no, it will not work. So at the end, because of receiving heat continuously, okay, vapor will be moved. And liquid will be less. This is the situation. Okay. So, example for this case, let's say your vapor quality I've shared with you earlier, maybe 0.1. Okay. Or even can be 0. Or let's say 0 to 0.1. X means it's fully wet. And when this is leaving here, X can be 0.92, 1, okay, 0.0, because 1 is the maximum of X. Okay, that is quite nice. Okay, saturated. So here to here means from the truck 10 just entered and truck 1 is just about to leave. So throughout the evaporate or the loading is being fully in operation. Okay, it's been fully operated. Yeah, so here to here, the receiving of heat the receiving of heat in this HFG4 HFG4. Okay, this receiving is in HFG4. Okay, HFG4. This QL. Okay, put this way maybe. This QL. I'm trying my best to explain this in different ways. Okay, slowly. I'm very sure during the lecture you will catch up this in any way of your convenient understanding. Okay, HFT. So if x equals 0 to x equals 1, the full HFG is received by one truck. Okay, let's say 1 kg. Okay, this all per kg you can see here. One truck you are receiving. If x is zero point 0.1 entering and leaving is 1, so then since x is not 0, that is zero point 0.1, so you are here the transport is receiving part of HFG, but transport is fully loaded, has to be. Or even x is zero point 0.1 to 0.9, again it's a part. So generally it's a portion of HFG. Portion of HFG that is being received by refrigerant, or what we call it the loading. Okay, what we call is the loading. Portion of HFG is QL. It's a so nice slide. So that's why we call it the saturated liquid condition. I put the wording here, saturated liquid conditions. Saturated liquid conditions. Okay. saturated liquid condition. So then you are strategically making use of saturated liquid to receive HFG. The beauty is throughout receiving, the temperature is 10. Okay? Temperature is 10. Or we can say this is 10 means what this 10 means. Evaporating temperature. Temperature evaporating because receiving heat by saturated liquid, what happens is more and more liquid turns into gas phase and still it's maintaining the same temperature and pressure. Okay? It's maintaining the same temperature and pressure. Okay? It's maintaining the same temperature and pressure. So 10 degrees C means that is the evaporating temperature. Okay? T evaporating. Or even you can tell it as boiling. Okay? No harm. Okay? Let's take this one. 10 should be here because the delta C. Quite interesting, Bhutana. Quite interesting. Try to look for a different color. No. Yes. T evaporating. Or even you can say 10 degrees C as T boiling. Okay. But standard usage is evaporating here when it comes to refrigeration, okay, or cooling technologies. We call it evaporating temperature. What evaporate? That is the transport, the working fluid, the 1 kg liquid trucks at saturated conditions, okay, that after receiving heat turns into gas at the same temperature and pressure. Okay, that's why. So when more and more gas is forming, when the trucks are moving towards the end of the evaporator or end of the loading, we have to make sure that the transport should be properly received for dispatching. That is very important. Transport should be properly received for dispatching, because otherwise no truck can come in. Okay, otherwise no truck can come in. That's why you have to have the compressor there as a dispatch solution. Okay, පුතා. කියපු ටික තේරුණාද? Can you understand what I explained? Can you understand? Can you understand? හොඳට තේරුණා නම් very good. බිම්සාර පුතා තේරුණාද කියපු එක? Can you imagine a bit? Is it difficult to understand? How do you feel it? චතුර තේරුණාද පුතා? Dilshan? Can you hear me? Yeah. ඇහුණාද කියපු එක ළමයි තේරුණාද? Okay. Can you understand? Okay. Very good. This one. Okay. It is actually a long pipe. Okay, it's a long pipe, but arranged as a coil. This is a very long pipe, arranged as a coil, and mostly done in copper or even aluminum, possible. No? So this is a long pipe. So let me do this piping this way by using two lines. Like this. Okay. So I'll make it big. And through this, the refrigerant is flowing all the while. Flowing. This is a long pipe, but twist and turn to have this into compact way. Okay, you see this as a block, but it is a long pipe. Okay, it's a very long piece of pipe. What happens? This is not straight. So in is there, in and out. In and in and out. Okay, so that is how the pipe is. Okay, this is some examples. It's a pipe somehow wound like this. Okay, there can even be a big ones. This for an AC solution, you can see. See the pipes all wound like this. But if you unwound this, expand this, it's a single long pipe. Okay, another one. See, in and out. So it's wound so that it can be compact. Otherwise, you have to have a very long pieces as component. You cannot handle, difficult to handle. Okay, so like this, like this. See one more here. See, end all turn like this. So you can have, see you, these are something like hairpins. Even you call this hairpin type. Hairpins all slot in and somehow loop on, and it's a continuous pipe. Okay. See one more here. So all you have in and out. Same like this, in and out. One is in, another is out. Here also you can see in and out. Okay. Some are very nicely enclosed. So very nice designs, but internally you see the same pipe. See, one shape is like this. I'll put it here maybe. See, some follows the shape to make it, to have this defined performance. Those are very big ones. And then externally put a very nice casing. You will not see this, and also it is very nicely housed for the performances. So this is a piece of one famous brand, Carrier. Okay, Carrier US. Okay, so here you can see inside the same coil. Can you see here? The coil, and you can see in and out. See, in, out. So I'll place it somewhere. So in and out. Here you can see in and out very clearly. See in and out here. You can see very clearly. See in and out for the convenient. For the convenience, both accessible from one side. See here in and out. Can you see? Okay. Even if I bend this one, so I can have the in and out from the same. Okay. Same. I hope you can understand this now. Okay. In and out. It's the same. So continuously flow in, flow out, flow in, flow out. It's continuous. Okay. It's continuous. Okay, I hope you can understand it very well. That's why here you can imagine trucks. Okay, you can imagine the flow here like this. See how nice Buddha. Okay, you can imagine this flow of 1 kg. Flow of 1 kg in and out. So first in, first out. That's why truck 1 is leaving. And last in, last out. That's why truck 10 is entering, but it takes time to leave. The relevancy. Example. Evaporator transport flow 10 kg per minute. So I just put 10 for your simple thinking. Okay, don't think too complicated this one. 10 kg. So I just take 1 kg by 1 kg. See how nice. Okay, so that's how it is. So now you can see that this is a pipe and this is a flow inside pipes. This is saturated flow inside pipe. Okay, so now you should understand that based on this, this is saturated liquid conditions. So this is a saturated flow inside pipe. Okay, let me add this word. Saturated liquid flow instead of conditions. Flow through, yeah, saturated liquid flow, that is enough. I believe you can understand this. From the practicals. Okay, saturated liquid flow. So initially, more liquid because vapor means already energized. Vapor means already energized. So little vapor means it cannot absorb anymore. until it will be superheated. So it cannot absorb anymore. So this small v is a passenger. Passengers, they are just sitting only, not doing any work. So v is a passenger. L is working, okay, in this working fluid. L is working, V is a passenger in this transport. Okay, in this transport, V is a passenger. No effect. That's why the smaller V at the beginning is good, and during this flow through this evaporator, of course, that liquid is turning into vapor gradually and become passengers. Okay, and finally the small L also will be receiving whatever left of HFG and will leave the evaporator. So you have to design this to match all. Okay, there are a lot of design aspects. You have to pick up those things afterward. Okay, so now let me take a snapshot of this. For that, duplicate this slide. I will do some cleaning. So nice. You can see three components. This return ready, the capillary you can see, your evaporator you can see, your dispatcher, compressor you can see. See how interesting this one, Putta, eh? It is quite nice. Nicely explain why you need saturated flow. Okay? Saturated flow. Now I will take some easy learning. This is very first lines. Saturated flow through this loading. Same way, saturated flow through unloading. Okay. Unloading also, this is a pipe. This brown color one is a pipe. Okay. It's a pipe. Let me show you. To go through. Let me take this part. that's also there. So now here unload. So the situation here from the previous lesson, now the flow is the other way. See, in and out. You can see. Okay. Let's say saturated. Let's say saturated. So here, of course, lot of energy loaded here, but in energy loaded in liquid form. Sorry, I made a mistake. In vapor form, okay? Energy loaded, small liquid. So release energy, more liquid, less vapor. After loading, it is different. L is the passenger. V has lot of energy and it's being released. Same. Okay. Same. HFG. QH. Okay. Here QH. Let's say basically saturated liquid flow. Very nice. Of course, there are little more clarifications you need. That is with some further exploring this. With some further exploring. And I will show you a condenser coil. I will show you a condenser coil. Why it's called condenser? Because the gas finally releasing the energy and turns into liquid means that gas or vapor, it is condensing. Okay. It's condensing. Some refrigerators you see behind this turnings. Again, you have in and out. So it's a pipe. Okay. It's a pipe. Nicely wound and arrange it. Otherwise, this will be a very long pipe. So very long pipe, you cannot, it's not possible to be with the compact refrigerator. No, refrigerator ka gedara pipe no paradike if you are not arranging this very well. So that's why you have to have that well arranged ones. Okay. So now I will not put that much because now you have little exposure. See, same like this. See, this and this, no difference. Okay. Actually, this is a component I have designed for an appliance, this component. The drawing you see. You can see some similarity. Okay. Here also you can see the pipes here, see. Sideways. Same way in the previous one. If you see this, see the pipes or ends. Yeah. This also designed by me one time. So you can say this. Okay. Again, it's a pipe. Okay. Again, it's a pipe. So you see some similarities in construction, that is pipes in and out. Okay. Let me put one more. Sometimes nicely put in a casing, but it is again this. See, well arranged. See the U-turns all so nicely arranged. U-turns all bends, bended with some fins. Smaller fins to enhance the unloading, and fan may be there together with this. Okay. Unloading. So you can see more gas, little liquid. Later, all the gases converted into liquid. We call this condensation. Okay, that's why now this is condenser. This is condenser. Okay. This is condenser. I hope you can understand. And I will share with you more condensers maybe. This is a website. Google search. You can see condenser coils. See, all pipes. Long pipe. Wound and arranged. And this fins like things. Here you can see fins. Other than the pipe, there are some fins for enhancing the unloading. We call fins. Okay, these are fins. See, fins. Fins are here. So this is the bare tube pipe condenser. So you can have some fins as well. Then it is fin tube, finned. Okay. I will show you the evaporator coils even. So you can design afterward. See evaporator coils I got from here. You can see a lot. See, different designs. Fins are here. Sometimes you have to do the frequent maintenance to remove the dust and okay. So we are learning something practical. Eh? See this one in and out. You operate the same, condense also the same. You will see in and out. Okay. Here also you can see one end here, another end is here. Somehow you can see. Oh, yes, this is one. See the manifold? In is here, out is here. Out should be here. If I'm not mistaken, yes, out. There are two ends. Yeah, in and out. See in and out, but here two ends you can see. So two parallel lines here, two sets combined. See in and out both should be here. So it's a tube. It's a tube. See, all tubes. One connected here. There should be another end as well. See the other end is here. One end, the other end. Okay. You can see it. Fins all to improve the heat transfer. Here for evaporator it is for loading. Even for unloading you have the fins. See? Very nice. Okay. See in and out. This is in. Here three parallel pipes. Single out. Out means dispatching the working fluid or the transport. So this goes to compression. Yeah. Later we have to learn how we do this dispatching. Okay. That is also very important. So now you can see it's a pipe as well. It's a pipe as well. So I will use this. No, not that one. Okay, let me use that. Copy. Paste. Hope it is okay for you. So well compact. In and out. You have to turn. Positive. Out. Okay. Trucks. Now, one is not in because first in, first out. Yes, that's it. Okay, condense. Good. Condense. Nice. Okay. Less energy after unloading. Let's say. I will leave the same color. That's it. අතන පුතලට තේරෙන්නේ නැති කියලා මේක. I believe you can understand this. Okay? I believe you can understand this. Okay? Next one is more challenging. Let me group this. Actually, I'm building your thinking approach very well, if I'm not mistaken. Okay? Slow, but for sure you will learn. Okay. See how nice. Dispatch or return through this component. I put a capillary here. It can be metering device. Now you know that. Two pipes. Because you see the pipe and some fins, mainly it's the pipe. Even though there are fins, it's a pipe, two pipes. Okay, pipes. I think that is no need. Nice. Good. Good. You know this condense. Okay. Good. Now again. 25 and 10. Okay, you see the room temperature 25 and inside the coil it is 10. That's how there. Okay, so you QL, QH. Take this. QH, QL. W. Okay. QL. Throughout. Because this is not 1 point. Nice. So you should understand this. Throughout the pipe, this loading and unloading taken place. Okay. Sorry. (10°), 25°. Okay. Heat pump into outside. I can have the figures here. See, 45, 30. Okay. That's why you should follow this presentation. So that is very important. Ambient 30. Refrigerant at 45. Nice. Okay. 10, 25. Okay. So for the transport, when passing through the pipe for loading, the temperature there it is 10 throughout till leaving 10. Transport, unloading, let's say in saturated liquid condition, entering and leaving is higher than 30. So we just consider here as 45. Okay, throughout saturated liquid flow, during unloading means energized vapor turning into liquid means unloading, because once vapor release its energy, it's become liquid. Low energy if I'm not mistaken. High energy means when liquid receives energy, okay, beyond the boiling point, okay, it becomes, not to say beyond the boiling, up to the boiling, and then turns into vapor, saturated conditions. Okay, so saturation, liquid flow. You can see only 19 now. Saturation, liquid flow. Saturation, liquid flow. Okay, Buddha? You should understand this very well. Yes, that's completeness. Sorry. That's a completeness. You can see. Okay. Refrigerant. I just put this way. The refrigerant fluid is like this, turning this way in this picture. Okay. But I have to be very patient. Here I'm combining both with a purpose. This HFG, portion of HFG, QH. QL, again a portion of HFG. here. Okay. -45 degrees C. I'm going to fill this. -10 degrees. Put it here. There it is. I'm going to fill one more. That's why your presence here is very important, because this following this thought process is very important. But we are sharing with our experiences. That's why it is extremely important, your presence here. Yes, saturation liquid flow. Now I have to take a transport fluid. So I will take, for air conditioning, this can be R600A. Later you will learn this. What is this R600A means? R600A we call. Even most of the time this may be at your home as well. Check what R600A means. I'm not teaching you. You look, there are R600A plenty at your home. Even in 10-12 kilograms. Look for this R600A. Okay. Now I'm going to share with you the screen. Because I'm looking for R600A now at your home. cannot say very well. Small a, small a. Let's see, I will take a snapshot. Whether 600 is here or not. Can you see this is 600? Can you see 600? This is at your home. Okay, this is at your home. So I duplicate the slide. I need one more. Okay, Putha. Now should be. Are you okay? Can you see it? This one R600. Here you can see R600. I'm going to take this out. So now again I'm going to share the screen. Earlier I mentioned about the Coolpack software for you for free download. So this is 600. Okay. This is R600 is saturation properties. Okay. You can see it here. Saturation properties R600. Here you can see. You see where you can see the R600D at your home. And that is not that pure quality, you know. For refrigerant, you need very pure quality one. R600. I have to make it small. How to say? R600D now. Anyway, for the moment, I will put it here. Back to sharing the screen. And sorry. And what happens? I will share screen. Can you see this? Okay. Just seeing this. So R600A, 45 degrees say here. At the unloading, transport is moving at, yes, moving, saturated liquid flow, temperature 45. So I will go to 45. 45, where is 45? 45. 45, so we are here. 45 is here. Can move it up. Yeah, no worries. $45. I will take this. At 45, you have pressure 6.102 bar. Okay, so that is what I need. So at 45, 6.102 bar, temperature 45, you can see. So I need that here. 6.102, because it is always very important to go with examples, otherwise you cannot understand this. Then another at 10. Another at 10. 10 is here, you can see 10. See 10? 10 is here. 10, what is 10? The transport temperature at the loading. This one, all closed. 10. What is the pressure? 2.219 bar. Okay, 2.219 bar. So I'm going to fill this here. Know that bar means pressure, you should know. Okay. 6.102 bar, 45 degrees Celsius. Okay. 45 degrees Celsius. $2.219 bar. 10 degrees Celsius. I hope you can see these real figures. Okay. Yeah. Because saturated. So you have a low pressure, low temperature. Because 10 degrees C, you have 2 bars. For you 45 degrees C, you have 6 bars. Okay. That's why for this kind of solutions of technologies, you have high pressure and low pressure sides. Color this. in black. Okay, so you have two sides. High pressure, low pressure. So you can see one component unloading related at high pressure, loading related at low pressure. Okay, high pressure side and low pressure side. High pressure side and you have low pressure side. I hope your screens are manageable. High pressure side, low pressure side. You believe me, learning a blend of technologies, practicals, and theories together in this way, it is very rare. So you should take this opportunity to join the class, listen to this and learn. Okay, that is very important. So you have high pressure and low pressure sides. Okay, very nice. And this high and low pressure is possible. Okay, and this high and low pressure, this low pressure. Let me go for a new slide for this. Otherwise, the slides will be. So this high and low pressure is possible. Okay, because of this two. Okay, the dispatching and return. The dispatching and return. Because of this two, high and low pressure, maintaining is possible. So the reason is this one has a huge pumping capacity to withstand higher pressures. Okay, not to say higher pumping capacity, but this has a pumping capacity withstanding means can pump for higher pressures. Okay, higher pressures. This dispatcher, it has a power to dispatch. It has a power. It has a power to have high pressure like dispatch so that it can be returned. Okay, and higher pumping capacity. So what the other component does is limit the pumping of dispatch. Okay, higher, instead of pumping I put dispatching capacity. Okay, higher pressures. You see the pressure here high, 6 bar, here 2 bar. So dispatching capacity withstanding higher pressures, this one. So what this does is limit the rate of dispatch. Okay, limit means metering. We call metering. So even though dispatch has a higher capacity, this won't allow that much to dispatch. So one is trying to pump, the other is controlling. As a result, there is a low pressure and high pressure sides. So for low and high pressure sides, these two components are responsible. Okay, these two components are responsible. So this two does the work, does the job of having two separate. Okay, because actually dispatching is doing its job, but the return ready, yeah, that's what makes it control, because otherwise there is no limit flowing, overflowing the loading. Okay, so there is a control. So that's how this flow control is being done, the return ready. Okay, so four major components and how they are working. Now you may have some understanding. So we are ready to go for the next slide, Putana. Okay. So now you can say the next slide. I'll share with you. I take this. That is too complicated. You focus on this right side. Yes, very nice. You can see here low pressure R602.19. The same pressure here. It's the same pressure. Okay, 2.19. So here it is high pressure. And here, after receiving energy, this is in vapor form. Okay, in vapor form. In vapor form. Okay, in vapor form. And then here becomes high pressure. Okay. Yes, now see what happens. Now see what happens. Let me add it here. Utara, be patient. Be patient. Good. Okay. I will show you this. This one also, there is an in and out. Okay, there is an in and out. So don't worry about the in and out at the moment. So I just put out this here. In. Also, I will put somewhere there's in and out. Okay, in and out. Yes. Okay, Putala. And the work done. W is here. Okay. Work done. W is here. So you can say receiving vapor. Okay. Low pressure, low temperature vapor. In vapor form, see low pressure side and low temperature also. Low pressure, low temperature. Okay. And here high pressure side, high pressure, high temperature. Okay. High pressure, high temperature. So this is in vapor form. Vapor form. Vapor form. And because of this dispatch power, this vapor is more energized. Okay. Because of this W, this vapor is more energized. Yeah. You can see that. This is another practical point. Because of W, the low pressure, temperature, vapor is more energized and becomes high pressure and temperature gas or vapor. That is what's happening because of this W. Because of W, so this happens, okay, because of W. Okay. So this is the situation because of W. So finally, this becomes high pressure, high temperature vapor or gas. Therefore, this process we call compression. Okay, therefore this process we call compression is the dispatching process for this case. Okay, so compression is the dispatching process. Compression is the dispatching process. The simple reason, so gas becomes high temperature, high pressure gas. So this corresponding, this component is called the compression. Okay, called the compression. So the component is compression. Dispatching process is compression. And since this is vapor compression, see vapor, you can see low pressure, low temperature vapor turns into high pressure, high temperature vapor mainly. So we call this, because of the compression, we call this vapor compression. Refrigeration technology. Okay. This is the technology, and then vapor compression. Okay, refrigeration technology. Vapor compression, refrigeration technology. And this system we call vapor compression refrigeration system. Okay, this is we call vapor compression refrigeration system. Okay, and at the other two components, you have this here. So this is the metering device. So the metering device and the compressor together makes this pressure difference, means makes this high pressure and low pressure signs. Okay, so this is pretty hard work, pretty hard work, and I believe you can understand this. So you have as I mentioned, the process, condensation. So this is condenser is the process, sorry, component, and the unloading process becomes condensation. Okay, unloading process becomes condensation. Okay, so this is the condenser, and loading process becomes evaporate. Okay, loading process becomes evaporate. Okay, good. I believe this is almost explain the vapor compression refrigeration technology. So we spent quite long time, but if you understand everything of this, even you can develop your own systems, solutions. This basic, without this basic understanding, if you need to get this, somehow it will take several years. But in few hours time, I put this text here with some explanation so that you can have some early understandings. Okay, Bhutana? Yeah, very good. Sorry. The next is we are going to understand further into the property variations, okay, and also some energy balances, because you already learned about the properties, the low pressure side, high pressure side, and the HFG energy interactions, okay, HFG energy interactions. So if I now, assuming you have some good understanding, so let me stop the class at 12:30, but before that, let me put a graph here for discussion for the coming session. So we mentioned some two pressures for R600A at 10 degrees Celsius. Okay. Here, I take it as it is. Another one. Here. High pressure. Okay. Okay. And here, I will mark the pressure line here. For the low pressure. High pressure side, I will mark the pressure line. Okay. And if I add a little here, R600A I have to put here because for different refrigerant, there can be different pressures corresponding to the temperatures. Okay. Quite nice. Okay. Yes. Yes. Okay. Now, in this case, this really says what's the beginning and what's the end. Okay. What's the beginning? What's the end? this really says what's the beginning and what's the end. Okay, what's the beginning and what's the end. Okay, what's the beginning and what's the end. So it's obvious this axis is pressure. Okay, this axis is pressure. P axis. Pressure. Pressure of what? The transport is experiencing. Okay, and the other axis should be energy. So energy here is the H, enthalpy. Okay, constant pressure processes. Can you remember? Work and enthalpy, there are connections. Energy as enthalpy. So pH graph. Okay, so this is now I'm marking the end point of loading because it is energized. Mark a bit big. I will marking the initial point of loading. I will mark the, because there is a compression process. Okay, dispatching receives more energy. Okay, so after unloading, energy level is like this. And believe if this is well balanced, the return through capillary, you should have the same energy levels. Or return, because it's only the metering device. And we should not expect any energy work interactions. Okay, so here of course we have energy work interactions. Okay, good. And let me take this dotted line. Front. So, because it's a constant pressure line, yes, I can extend this until there. So I will format this with little heavier. line color, if I put black, would be much better. Okay. So the same way, the line here, I will put like this. Okay. So you can see the pH energy interactions like this. Okay, constant pressure, two lines, low pressure, high pressure. Let me help you with little more additions. Compressor is here. The work done. Okay. Give me 5 minutes, Buddha, to complete this. Your metering devices. It is only doing some controlling. So compressor try to receive and dispatch, but this controls. So insufficient supply because of this control. Receiving side of the dispatch pressure drops. Very nice. So this is to evaporate. Okay. Let me put it here small. Pressure line. Never mind. I put it here. Where is the dispatch? Sorry, unload. It is here. I put it. Cannot make it any more big. Now should be okay. Also, all the four components, there are in and out. This one also in and out. This also in and out, in and out. You have noticed that. See, in and out, in and out, in and out. So here, for the energy balance, okay, energy balance. Balance. You have to use steady flow energy equation. You have learned this. Steady flow energy equations. Okay, you have to use steady flow energy equations. I will take QH, QL W. QH is here. QL is here. Where is W? Oh, W is here. W is here. Okay, W is here. And then if I take the points starting from dispatch, this is 1. This point is 2. This point is 3. What happens? 3. This point is 4. Okay, so your QH will be, okay, you have to prove this because you have learned. You have learned this. Remember, you go through your notes and my explanations. QH is H2 minus H1. Okay, so H at 2 minus H at 1. But remember here, for this graph we are considering for 1 kg transport. Okay, so your expression for this is small qh, H2 minus H1, this is for 1 kg per kg transport. Okay, per kg. That's the situation. No? QH. Okay. For W, I put sorry, I made a mistake. H2 minus H3, not 1. H2 minus H3 per kg. I put it here. For big W, H2 minus H1. H2 has more energy, you can see. Because after loading, dispatch also provides some extra. So W, simple W, H2 minus H1. Okay. QL next. After writing this, I'm going to stop the class today. QL. So at H4 level, receiving Q will become H1. So QL is H1 minus H4. So you have to look into your notes as well. Okay. You will see this very clearly. Yes. And one more here. At the metering device. H3 and H4 are the same because QL no QL, sorry, no heat, no work interaction. So H3 equals H4. This is another one. Belongs to this. Compressor belongs to this. Condenser belongs to this. To evaporate belongs to this expression. Okay. To capillary is this. Very nice. Let me do some housekeeping here. Good, Butala. So we have 12 students now. So this is the manageable and its expressions. And we have learned all from the very beginning. I believe it is done. Okay. Let me leave it there. My right should be here. Yeah, Puta, that's all. For today, this is a big work today we have done, but we have a lot of homework. चला ये भी email लगाती है ना, so you have to do it and submit by. Today I mentioned maybe 7th, if I'm not mistaken. Anyway, let's check the timing. So today we have reached almost a milestone. So next week we will do some questions, and also we will learn more about the pH charts for refrigerations, and we will do some calculations. Okay. Also, we will construct some pH charts, and we will learn about different refrigerants. And we have realized that this is vapor compression technology. And you should know why we call this vapor compression technology means because of the specialty of the transport. Yes. So, lot of things we can learn. I forgot to teach you about the relationship of flashing for refrigeration. Maybe I will share with you this one again in the coming session. මම කතා කරන්න පුළුවන් දැහෙනවද පුතාලා කොහොමද තේරුණාද කියපු ටික? Are you all right? බිම්සර තේරුණාද පුතා? ඈ? At least 50%. Very good. චතුර හරිද පුතා? මදුෂානි okay. ඉසිවර okay. Maybe Sajid received a call. That is okay. ධනංජය පුතා තේරුණාද? කියන්නකෝ. Are you okay? Actually, once I teach, I should not ask whether you understand or not, because I have to. I should teach you to make sure that you should understand. ගුරුවරයෙක් හැටියට මේ තීරණාද කියලා අහන එක එච්චරම රෙලෙවන්සි එකක් නෑ. But because of the gravity of this, and because of the challenging of explaining this, and because of the challenging of building this concept together with you, it's a quite challenge for me as well. That's why I'm asking whether you understanding this or not. We have discussed a lot of the technical things. You have a lot more to think. That's why, because of this situation and this kind of this level of class, even I am compelled to ask you Terunada, whether you understand or not. Because that is so tough for you and me both, Putala. If you understand this, you're excellent. Even if you don't understand this to the fullest, you know that there are many things to understand. So the textbook refrigeration and the refrigeration I have discussed here. The feeling is much better in this sharing. That's why these are not in the books, and it's not possible to put in the books. Additional one arrow came by, right? There shouldn't be an arrow, but that is also okay. No issue. I think you can have this as well, because we have explained it to the fullest. It is okay. Now that is flashing. So I think we are in a solid move to understand the cooling technologies. And once you learn this, power plants, steam power plants, nothing. Okay, nothing. So it's a matter of 1-2 hours even to do big questions. Okay, big sums. Yeah, that is not a big deal. Everything looks simple because this is the hardest part, to comprehend, to understand this Pathala. Okay, very good. And thank you very much for staying with me for so long, children. So hope you got something. Yeah. Samadhi Terunada. Samadhi Munasingha. Uta Terunada, did you understand this?
Yes, sir.
Okay, happy that you said yes. Very good. Now that is what I need. But don't stop from here. Because the best appliances, cooling solutions are yet to find. So you are the ones doing this in future, and without this knowledge, it is not possible for you. So you know how artistic the technology is. how artistic the science is. It is quite belongs to nature. So at least I'm very happy to share at this level with you, and you should be lucky enough to see thermodynamics in this way. So that's it. So see you next Friday, and if possible, Puta, try to arrange a class, extra class, because I'm happy to spend the time, because this is a very important subject. That's why. So if you can arrange an extra class, but before that, make sure you drill this very well. Even I will upload this lecture also to this links, and I will let you know. Puta, read this. Read this, understand this to the fullest, and have this as your own knowledge. Yeah. So today we are done up to very good levels. Yeah. Happy that you have good capacities to comprehend this. So that's all. Any more comments before stopping? So wishing you all a very good new year, 2021. And start is, of course, is very solid. For learning point of view, even you have learned the knowledge that no many lecturers knows, you know. I'm not boasting. Yeah. With no many lecturers knows in Sri Lanka. So you are really lucky enough in that sense. Try to capitalize this opportunity by reading this, drilling this, realize this, and it is well beyond book knowledge. And then later you feel that book knowledge is peanuts, nothing. Okay, Buddha. The manufacturing representative and mechatronics representative, Putana, if possible, try to arrange a session so that we can do this in style, and we can even finish this fast. Advanced sessions are very good extra, because we can make sure that we are learning to the fullest. Study sticker. We have to stop. So we have to stop halfway. That's why. Since we are drilling the subjects, we need little extra time. So running with පුළුවන් බලන්න මේ සතිය තව extra session එකක් ගන්න. Yeah. හරි නේද? ඔව්. බිම්සර පුළුවන් නේද පුතා කතා කරලා ගන්න? You talk to your representatives. පුතා කතා කරලා ගන්න. හැබැයි before that, try to understand this to the fullest. කතා කරලා ගත්තා leasing එක. This is a 4 credit one, and even this is more than credits. You can do a lot of projects out of this. Yeah. Okay, Butala, then. Thank you very much for staying with the class. Good luck to you all for the new year, 2021, and take care, and do the studies very well. So, bye then, Putala, all of you. Bye. Bye. Take care.